think we're good here time-wise. Last session, y'all hanging with me here? These are long sessions, probably longer for you than me. I'm talking. You're gonna have to listen to this stuff. I hope it's interesting to you. So we're going to finish up with some fluidization and kind of show you sort of where we're at. I had a number of, I just thought, excellent questions during the break, which I'll just try and summarize a couple of those because they'll be important for other people. So you say, well, in coal, what about ash, right? There's ash in coal. What happens to that stuff? Well, it's actually not as bad as you would think because ash, when you burn coal, is going to be smaller and lighter than the parent coal, and the carriers that we're talking about are dense and large, all right? And so if you just blow air over a bed with ash and the carrier, the ash will come out. It'll just get entrained into the gas flow. And I'm not saying that just as a maybe. I mean, we've tested that in our lab and it looks pretty good. But I'm cautioning it's not been demonstrated in a real system yet. That's why this is still at a research level and not a developed process. So there's an excellent question about how you handle the ash in the system. Somebody else asked me, could you mix different size carriers or different size materials in fluidization? And the answer is absolutely you could, and that's how you would separate the ash from these larger coal particles. So it's an excellent question as well. And you know, there are a number of things you can do with different particle size in terms of separating materials out. So let's jump right back in and talk about different types of gas-solid reactors. Again, if you find yourself working in this area, or maybe you're doing biomass combustion, you'll want to be familiar with the terminology here. So you have up on the top there a fixed bed reactor. That would be, for example, like what has always been called a stoker, where you have a grate, almost like a barbecue grill, where the material sits on that. And this was the way coal was burned for many decades. There's not many of these left. You can still buy a few of them. And then bubbling fluid bed, where the velocity is less than the transport velocity, so the particles stay in the bed, but there are bubbles moving through that bed. And there are large boilers that are built using bubbling fluid bed technology, and you can take the heat out like right in the bed there or up in the convection pass. And then circulating fluid bed, which I have shown on the schematic there, this is very much like the chemical looping that I described, because here you run the velocity higher than the transport velocity. There's a region here where you have a physical bed, and then it gets less dense. Particles are continuing to react here to get carried around and separated out in the cyclone and then circulated around. Okay, so that's the style of circulating fluid bed. This economizer, some of this works on the convection pass here, pulls heat out in both this region and this region. And so that's a circulating fluid bed. Also, for the fluidized catalytic cracker that I described earlier, that's another example of a circulating bed. The material actually gets kicked up into this region and comes back down. It circulates around. Moving bed, a little bit different. Not as many of these in terms of different applications. Most common one is what's known as Lurgi gasifier. It was taken over by Sasol now. But anyway, the idea there is you have very large particles and they move counter current to the gas flow, which is moving through that bed. And you know, that has real advantages for chemical looping. I think Arnaud and I were talking about reactor design just a little bit ago. And what that does is it puts, for example, in chemical looping, if you have the carrier raining down the top with gas coming up the bottom, you have fresh carrier, lots of oxygen, working up against that fuel which you're consuming from the bottom. So you have the highest oxygen content where you've got the lowest CO2, which is what you want to consume all that CO2, right? Counter current. And that's what you do in a moving bed design. And in chemical looping, L.S. Fan and his students at Ohio State, they have really, honed the art of developing that as a concept for chemical looping combustion because of that counter current behavior. So that's one way you can arrange the bed. And then, of course, in train, there's no bed like in a pulverized coal boiler. You just put the stuff into the airstream. It's conveyed with the airstream. So these are some of the, the terminology that you'll see for different types of gas-solid reactors, both in the chemical industry and in the combustion industry. So the discussion we just sort of finished up there, it's covered really the hydrodynamics. The process of designing a chemical looping combustor is actually a lot more involved because you've got to think about chemical reactions, conversion, how do you get the heat transfer out? And so the question is, if you want to design a chemical looping boiler, what combination of reactors is the best one? And I don't know. I mean, this is really something we are debating right now. There's a bunch of trade-offs between a large and a small oxygen carrier, both in terms of the kinetics of the rate on that carrier as well as the fluidization, the hydrodynamics of the bed. So you got a lot of issues to trade off, and you can conjecture on many of these, but really, we're at a stage of development where you're better off looking at using CFD. Now, if you don't work in fluid beds, you might not be aware, but we have very good fluid bed codes today to predict the behavior of beds. And so you can see that's a simulation of the fuel reactor in our experiment, and you can see the bubbling behavior. We'll see the bubbles in more detail in just a moment, but you can see how turbulent the material is, and you're trying to convert that and react it with the fuel as you move on up through there. If you work in this area, I just have to brag on my colleagues at NETL because they have the open source code that's most widely used. It's kind of like if you're in engines today, Kiva is the code that people have used for engines. MFIX is the code for multi-phase that came out of the labs, and my colleagues are actually developing that and continue to develop it. So just to prove that these codes actually work, will this play? Oh, it won't play. I just thought this was a very good slide here. I'm going to get the movie here, and it'll show you the kind of the state of our ability to predict the behavior of these fluid beds. The photo, or the, why is it showing something different than what I'm seeing here? There we go. Okay. All right. So the movie that you're looking at, this is actually a lab experiment from our lab where this is the air reactor. You can see the fluidization happening here, the particles getting carried up, knocked out in a cyclone, fed into this reactor, which is really a loop seal. That pipe extends down to the bottom here. The bed's being filled, and then we're fluidizing from the bottom. When it gets too full, it dumps over into here. This is the region where if this were a hot system, we would add enough air to fluidize it and kick the ash particles out of the bed, all right, and then you'd collect those, and then the thing actually spills in this design out the bottom, I think, here, up through, and then that forms a loop seal to keep this separate from the airstream over here. All right, so the fuel would actually go into that bed. Let's just keep that going here. There we go. So the fuel goes into this bed. This is an ash separation. This is a loop seal, and then you go back around to where the air goes around. So that's the physical experiment, and this is a CFD simulation of the exact same thing. And what we've done is actually made the particles bigger in the simulation, so you could see where they're going. And they showed that to me, our modeling group. Like, wow, that's pretty impressive. And I started looking at it. You see anything different? Take a good look. Yeah. Yeah, so a big difference in the height there. I thought, see these modeling guys, right? They just can't get this right, I think experiments are really good. So I was thinking I could really, go complain about this. We had the thing set wrong, in the experiment. So we fixed the experiment, we got to the simulation results. So my point is, at least the hydrodynamics, you can do a really good job of predicting that, all right? So all you experimentalists, we had our field day there. We're done now. All right, so here's the next little part of this. How do you design these reactors? Get right to the right slide here. Okay, there we go. So this is an interesting question. Where do you take the heat out of the process? All right, because we've looked at different carriers, endothermic. For endothermic carriers, you don't need to take fuel or heat out of this side, because you might actually have to take heat out. Exothermic carriers, you've got to take heat out of the air reactor, right? No matter which carrier you're using, you've got to manage that air reactor exotherm. Well, we're not going to have time to go into details here today, but I just thought it'd be useful to get you familiar with some of the issues we're sort of grappling with. The air reactor heat release could be quite significant, right? Why? You're burning a metal, right? It's like, you ever see a cutting torch? You better be careful about how you do that process, because it is like a cutting torch, right? You're oxidizing, for example, iron, and so there is potentially a lot of heat release. So you got to think about how you're going to take the air out of that. And so how do you do it? Well, in a conventional circulating fluid bed combustor, an example of one here, you know, I showed this before in a more schematic way, but the fuel is injected at the bottom. It's carried up. There's heat being extracted by the walls of the device here. You separate out some of the char, and there's sand in there that you're using to moderate the temperatures. Then there's a heat exchanger right in this portion of the leg that takes heat out of the solids right at that point. Then you keep re-injecting any unburned carbon at that point, as well as the bed material itself, which is ash and sand. And then you actually take some of the heat out from this convection section down here before going out the back end of the thing. So chemical looping has a lot of similarities to what you see there, and you think, well, why can't I just make it like a circulating fluid bed combustor? It looks almost the same, doesn't it? I mean, it should be about the same, but there's a few little subtleties that get lost when you say it's just a direct analog. First of all, over here, the carbon goes around a bunch of times, right? You don't have to burn all the carbon right in this reactor because it's going to get separated out and sent back in. Remember I said about the carbon coming over in the air reactor? You can't do that, or the CO2 is going to come out on the air side. So right away I'm starting to realize there's a difference between that and conventional practice. And in fact, this is where my little analogy of metafuel, remember, starts to pay off when you think about what you're doing. Conventional CFB combustor, as I said, a lot of that ash contributes to the bed material. You could deliberately put sand in there to help moderate the temperatures. So the solid fuel going up that riser in the CFB combustor, it's mostly inert particles with a few particles of fuel in there. There's only about 2% mass of these, and the rest, the 98%, is all these guys. In a chemical looping combustor, I just have metal, my carrier, to react. So right away you look at it, it's like, wow, that's really quite different because there's not that inert. I could put inert in there, but you know, that's a design choice that I haven't made yet. So, you know, the potential for the temperature rise here, I've already said, is pretty great because you're burning metals. So what's the difference here between this, you know, CFB boiler and chemical looping? Well, if you just plot up the reactions that we're talking about here, if I look at a metafuel, remember I say we're making these iron carriers are a metafuel, and then I compare at the bottom carbon fuel, and I put the reaction enthalpy per kilogram of fuel plotted up over here, and then show it on this graph. So these are the different carriers. 1, 2, 3 are all iron. Here's copper. Here's calcium sulfide, sulfate that I'm going to burn to make sulfide to sulfate, or carbon. You see right away, well, carbon on a mass basis, a lot more heat release when I burn that compared on a mass basis to some of these other carriers. So, you know, these so-called metafuel particles, there's like 30 to 60 times less heat than over there, but there can be significantly more of them, right? That's what I was showing up here. I don't necessarily have all that dilution. So even though they don't have as much heat release per unit mass, how many more of those are flowing up the system? And this gets a little bit detailed for late on the afternoon here, but I think you'll catch the point I'm trying to make. If I wanted to design it and say, I don't want the hydrodynamics to be a complete new scheme. I'd like to make it look like what I already know how to build, circulating fluid bed combustors. So what are some typical flow parameters for a CFB system? Well, if you go into this reference, all right, the one I mentioned earlier by Basu, he gives you lots of nice numbers that you can actually use. So I reproduce those here, and if I look just at a boiler application, if I pick his superficial gas velocity, about 6 meters per second, multiply by the air density at the temperature, here's my flux of air flowing up that reactor. And this is just a typical number. It can be a lot higher or a lot lower, but I'm just trying to give you some sense of scale here. And then if I look at the circulation rates for solids that go with that air flow rate, all right, that's about, there's 2 for the air. The solids turns out to be about 10, so the ratio of 2/10 is 5. That's the solids mass flux divided by the air mass flux. Typical number might be 5. I almost hesitate to say typical because it could cover a wide range of values, but I'm just trying to give you an example here, right? So remember that mass ratio of solids to air being 5 for a typical CFB. So what happens if I want to build not a CFB, but a chemical looping system. So again, remember here now, with chemical looping, I haven't necessarily put any inerts in there, so I just have all of my metafuel particles flying up that reactor, okay? So let's see what I get here. All right, relation between these two. Here's the solids flow rate again, solids to air mass flow rate, and then here's the stoichiometric fuel, which now we're saying includes a metafuel, to air. So this is the fuel-air ratio for these different metafuels as well as carbon. Well, look at it up here for iron. It's 6.7. All right? In other words, you need a lot of mass flow of iron to consume air at a stoichiometric condition. It's very different from what you encounter with hydrocarbon combustion. Right? Hydrocarbons, like carbon down in here, 0.08. All right? So you don't need a lot of coal mass flying up that riser in a conventional CFB, and that's why most of that material going up the riser is actually inert. You get to a GS-GA ratio of 5 in a conventional CFB because most of the solids are inert. Well, what has it got to be in a chemical looper? Look at that. To get to stoichiometric, for some of these, it's like 6 up here, right? So the point I'm trying to make is with these chemical looping systems, there's a lot of solids that you're going to rise, and it could all be carrier or not. You could dilute it. But there's a catch, all right? And this is where it gets really interesting. You could operate it very dilute, all right? Don't put a lot in there, all right? So you wouldn't have enough in there. But you have to remember, it takes time to convert the carrier. It's not like a carbon particle. Go to this next slide. So this is the practical issue, all right? In a chemical looping system, some of these reactions, the time that it takes for full oxidation, a lot greater than 10 seconds. A CFB riser is 5 seconds, and that's on like a 40-meter tall system. So right away I'm starting to see, well, that means if my carrier goes a lot longer than that, I actually need a lot more, remember I talked about active density, to get to the conversion rates that I need. It's very different than what you would see in a conventional combustion design, right? Because I'm saying, yeah, you can lift a lot of material and it can be all carrier up that thing, but it's going so slow, you actually need all that to get to a reasonable rate of conversion. You won't convert it all, but you'll have enough when you go over to the fuel side, and you'll bring enough heat over with you for an endothermic carrier to do the fuel conversion. All right, so this has been really complex. So I've tried to lay out the competing issues of the hydrodynamics to lift the material with the requirement that you have a stoichiometry to meet as well as a thermal balance to match up. Sounds like it would be very hard to design one of these. That's the point I'm trying to make is we haven't decided, well, what is the optimal way to put one of these together? It depends on a lot of different factors. And there are a few other practical issues that end up, I've already talked about this one. Use an external heat exchanger is one way you keep the temperature rise down in, the transport in the air reactor. You could also add, I'm sorry, that's that one there. You could also arrange 2 interconnected loops, all right? And that's my figure C right over here. Let me explain this one. If you have this as the air reactor and you loop around, it looks exactly like a circulating fluid bed combustor. I haven't said anything about fuel yet. I'm just burning this reduced carrier. It's going around in a loop. And I just split off a portion of that as the process is going over to the fuel reactor. It goes around a bunch of times over here, and you send it back. So the advantage here is you get as much residence time as you need, within reason, going around these loops, right? And you take off just what you can afford to go over the reactor. The disadvantage is you have a lot of circulation going around each of those loops many, many times, potentially 4 or 5, 6 times. But it gets you out of the problem of I didn't get enough conversion, I can't balance my thermal with my hydrodynamics. So you start to understand there's quite a few trade-offs when you want to put one of these things together. So maybe you've got a better idea in terms of how to arrange these devices. And this is really a research issue. Maybe if you think of it, come talk to me or give me a call or send me an email because we're debating what's the best way to put these things together right now. What's your idea? Well, maybe moving bed. I mentioned Professor Fan's group at Ohio State. They've really looked at that very hard. It looks very promising. Addresses some of the issues I've described today. By the way, in terms of that last idea of sort of looping around in the reactor, I just threw this slide in because it might be useful, you know, if you end up working in this area or other areas as well. You know, what I'm saying is you can circulate around that reactor a bunch of times. And so here's just the air reactor with some nomenclature to indicate reactant going in, reactant coming out, looping around. Here's the equivalent topology of that. F is the fraction, single pass fractional conversion. How much does that material get converted going through here? R is the recycle rate. And so if I plot up the reduced state flow out versus in, what I want to have happen is I want to start off, if there was no single pass fractional conversion, I wouldn't have anything being converted. It would come out with the same amount out as going in. If I had complete single pass fractional conversion, I would actually, all this stuff would be reduced. That's 1 at this end. This straight line here is just one pass through the system, no recycle. And so you can see the two are directly related going through that system. You can work the math out here. But as you go through, I think I've got 1 recycle loop, you know, per flow, 2, 4, and 8. So here you get down, you know, if I had a single pass fractional conversion, maybe I could only get like, I don't know, 40% converted on a single pass. If I take it through 8 times, I can get less than, you know, 20% left that I haven't converted. So it's just, that's the math of, yeah, if I go around a bunch of times, even just a few times around that loop, I can convert a lot more. I don't have to depend on just great single pass fractional conversion. This is all nasty chemical engineering stuff that I didn't learn well in school and had to learn later. But anyway, so let's, you know, wrap up today. Finally, in the last couple of slides here, you know, what's happening right now. This is more just fun and, you know, general interest things that are going on in our laboratory right now. There are a lot of groups around the globe that are working on chemical looping. Chalmers, I think, certainly one of the leading groups in Europe. Darmstadt's got a very interesting chemical looping device. Ohio State, Utah, here in the U.S., all over. A lot of different groups doing work, including our own lab. Commercially, Alstom's developing this here in the U.S. Babcock and Wilcox working with Ohio State. There are probably a few I've forgotten to mention there, but anyway, there are a number of groups working on this. The stuff we're doing at our lab is shown on this slide, sort of summarized quickly. We have focused a lot on developing validated simulations. So to do the simulation validation, we actually have a full-scale chemical looping system. It's shown here. That's probably about 20 feet up to the top there. It's fully refractory lined. We have simulations going, and I showed this one earlier, of the actual looping process along with the kinetics that we're loading in. We've got 0D models, all that type of thing. And one of the things some of my colleagues have done is develop carriers. Some of these are really interesting. The one shown at the bottom here is actually thermally neutral. And if you remember the talk earlier, what that allows us to do is not worry about managing the heat that we need for the fuel reactor. So it just goes over there, it reacts just due to the change in the partial pressure of oxygen, releases its oxygen. We have not tested this one in the full loop yet. That's still on the way. This one's been under test and just completed a series of runs actually earlier this month with some interesting results. It's all good. One of the things we're doing also then, and I'll get to this in just a second, is measuring things like attrition. We have cold flow models to look at validation in the numerics. And then the techno-economics I'll get to here in just a second. So here's sort of what we've been seeing in the lab. I mentioned the thermally neutral carrier, and you know what we're wondering about is, because you don't have to set the flow rate for that carrier to provide the thermal energy, it actually reduces the amount of circulation rate that you need. And will that reduce attrition? I don't know. We're going to find that out. It's part of what we're looking at right now. What we've seen in terms of the CFD predictions, I gave my modeling friends a bit of a hard time there, and then had to eat crow because they were doing pretty good on the cold flow. What we've seen is actually in some of these portions of the reactor, the parameters that go into the CFD are very critical. And so we found you can get factors of 2 and 3 off in terms of predicted circulation rate because of parameters like the so-called friction angle for the particles, which is something we just have to measure right now. We're not at a point yet where we can predict that. So people that are working in fluidization, that's an active area of research to try to improve the prediction for some of those parameters. I'll mention, oh, and of course, obviously what that means is we really do need validation data in the hot flow cases. That's why we're running these experiments. These are generic experiments. We're not, you know, focusing on any particular design here, but we need a good enough CFD model that we can predict the designs that we're interested in. We are developing some sensors to actually measure the hot solid circulation rate, which remarkably is not something people know how to measure today. There just isn't a technology to do that at temperature, even in existing CFBs. Well, you get around it in a CFB because you can just change the circulation rate and balance temperatures. Here, that circulation rate is basically your fuel-air ratio. So when you're trying to control to a set point, and you have a system with a thermal inertia that's on the order of tens of minutes, it's pretty hard to control exactly and avoid a lot of CO or over-reducing your carriers, a lot of issues. We really would like to measure it directly. We don't have a technology, but we're doing a microwave sensor that we've used it successfully in cold flow, no doubt about it, and we did test it last run in hot flow, but it's still not a technique that's known well. If any of you are working in sensors for high temperature solids flow, please give me a call. We'd like to know how to do that, and so would a lot of other people. We had a whole bunch of lessons learned as we were getting this thing operating. You know, I'll mention the ability to separate the solids out in that cyclone. It sounds easy because you can get cyclones with a 99.99% efficiency. You can get them, you can buy them, you can make them, manufacture them, and we achieve that here until you realize how much solids you're circulating here. 99.99 means in a number of hours you've lost a significant mass of small material, which in a real process you would recycle and put back in because you'd catch it in the bag house. In a lab environment, it means your experiment's done, right? Because you just lost all the material out of the top. I mean, we've run these tests for multiple days. So separation efficiency starts to become a practical issue that drives the design, right? And we actually found a great way to address that, which I won't get into today. Now, the thing that we are looking at right now, very interesting, you know, bubbles matter. Everything is always learned the hard way, so here we go. We knew this was an issue, but I don't think we appreciated how significant until we actually ran, you know, a few experiments here. And so this is, again, the reactor that you saw there that's running in our laboratory. This is the air reactor coming up through the cyclone. The fuel reactor, there's a loop seal here, fuel reactor. This is the CFD of that same thing. So I'm going to show you what happens, not when we're operating hot, but after we took the thing apart and then looked down in that A cut down there. So you're looking down at that. This is a rag that we plug the outflow that's just laying in the top of the fluid bed. So here's what happens when you actually fluidize that environment. Okay, so there you can see the bubbles breaking through the top of that bed, right? It's a bubbling fluid bed. It's what you'd expect. So why is that so interesting or compelling? Well, this was actually a test on natural gas. If you put coal in there, you'd have the solid reactions. The coal you could keep in the bed, but you can't keep the gas in the bed, right? You pyrolyze the coal or you gasify the coal, it's going to go into those bubbles, all right? So this is the tricky part then. As those bubbles leave the region where they would contact the metal oxide, what happens to them? There's no oxygen in that region. Nothing happens to them. They go out the exhaust where you don't want them. So bubbles matter. You have to keep that gas in a bubble long enough to let it react with the material that's flowing around the sides of that bubble. You think, I know what I'll do. I'll make the bubble smaller, all right? Well, yeah, you can do that if you slow the flow rate down. But then you have to make the reactor bigger, right? And you can't make it, you know, infinitely large. So you think, well, why don't I just make the bubbles smaller by redesigning the injection? That's what I would have thought, right? I mean, that's what you do if you're a regular combustion engineer and you're doing gases and liquids. Well, it doesn't work that way in fluidization. The movie I'm going to play here is a simulation of the fuel reactor. It actually isn't the same one that you're seeing here, but the details aren't important. So it's a little bit smaller one. But we have on the bottom here to fluidize it a porous plate, and then we have discrete fuel injectors. and we did different geometries. You know, one geometry here, this was a little bit smaller, and then even more injectors here, so different injectors. So watch what happens when I play the movie again. Porous plate on the bottom, no discrete injectors, then different injector sizes. Look at what happens to the flow rate above the point of fuel injection. So if you look at those bubbles, do you see much difference in the size of the bubble that's coming out of the top? Unfortunately, I didn't. All right? And they look a lot like, as they emerge at the top there, they look a lot like what you see in the actual environment where we're running this process. So the point here is, at a given flow rate, the size of those bubbles is more or less determined by the hydrodynamics of the process. You can try making the bubbles smaller, and they'll be smaller right where you're injecting them, but they will coalesce to a natural size. It just has to do with the instability that says it's at that flow rate a requirement to have a bubble moving through that fluid bed. You can change the bubble size if you change the particle diameters, or as I said, if you slow the flow rate down, you know, they'll have to get a little bit smaller. But it's something that you need to think about, because I have to have enough time for the gas that's in that bubble to react with the carrier. Because if it doesn't, it's going to come out the top. All right? So again, answer, make the bed taller. Well, what happens if I make the bed taller? The pressure drop goes up. See, I'm starting to really paint the picture why I'm struggling to answer the question, what's the best design here? It might not be a fluid bed. It might be a circulating fluid bed, a much taller reactor, but you still got to get the gases that are left from the coal volatilization to react with the carbon that's in there. So it's an interesting problem, you know, for combustion design or reaction design. How do you make these systems? Now, how do I... Next. Okay, there we go. Almost ready to wrap up here. Wouldn't be complete without talking about like the economics of what would it take to actually run a chemical looping system. So this plot shows the results of some work that we're doing. This was for a techno-economic study showing what happens for a natural gas fueled chemical looping boiler. And what we did here is we studied a number of parameters that we could control, all right, or just set. All right, so we're saying if I had better carrier reactivity, if I increase the carrier reactivity, what happens to the vessel height or diameter or circ rate or blah, 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 and ultimately the cost of steam. Well, I think you'd expect if I had a more reactive carrier and I increased it, it would have a large impact on the vessel height, all right? And if the carrier activity goes up, the vessel height goes down. That's what the plus minus means. Does that make sense what the plot's showing? If I increase that a lot, there's a big effect and it tends to decrease the vessel height. That makes some sense. And you can go down and rationalize how all these different parameters, you know, affect things. Obviously, if you increase the reactor velocity, it has a large effect on the vessel height. You increase it, the vessel's got to be taller, right? So that's why it's a plus and a plus. Well, you can go through each one of these, but the one that's probably the most important, the cost of steam. You know, how do any of these parameters affect the cost of steam? The only one that has a significant impact is how much carrier you lose. Why is that? Well, because the rest of it is just capital, right? You're just buying steel and refractory and you're putting it together, right? But the carrier is really, in the way you're doing this process, it's like a fuel that you're putting in, isn't it? That's the stuff. So if you lose that, it costs you a lot of money. And that's the biggest parameter to be concerned about, is the cost of losing that carrier. You could have an expensive carrier if you didn't lose any, right? Or you could have a cheap carrier and just let it get all chewed up and throw it away. But this is a very important issue when people talk about chemical looping. How much carrier do I lose, and what does it cost? So that's why going forward, we are really focused a lot over the next year or so on understanding how do I avoid losing the carrier. So we're just about on time. Let me be a little bit ahead. Good deal here. So something to think about now, all right? Because I put this chart up way at the beginning just to make a point. We're finally back to the beginning here. And, you know, I showed, well, most people think about carbon dioxide capture in terms of, you know, how much work does it take to do this separation per kilogram of CO2? All right? Well, does chemical looping fit this description? It doesn't really, right? Because it's not something you add on. It's just inherent to the process. There is some work that you would need to compress the CO2, right? If you were going to store it, you'd have to pump it up to pressure. So you don't get that number to 0. But what's a drawback to chemical looping with respect to this box over here? Anybody take a shot at that? I haven't said it, so if you don't get it, but I want to pause for a minute and see if you think about it, because there is a drawback. You know, I'm actually really a combustion guy for gas turbines. It's really my real passion, all right? The thing that's so different about this area is the temperatures, right? I'm operating these devices at about 800 centigrade. That's really about the hottest you're going to be able to do it. And the steam cycles today only, I mean, you're still getting a big exergy destruction getting down in the steam cycle. Even in the best systems, doesn't even get to 700 centigrade. That's the highest temperature you're going to get in terms of the working fluid. Gas turbine is what? You know, really, really high compared to that. 1300, 1400, 1500, way higher for the top temperature. So right away, if I say I'm going to do chemical looping, I'm saying I'm stuck with a peak temperature for my working fluid of maybe 600-700 centigrade, might be 700. So the efficiency of this front box is handicapped by the fact I'm doing this process at only 700 in my working fluid. That's why there's people that have talked about, well, could I take chemical looping and combine it in a gas turbine cycle somehow and somehow raise the temperature, which I don't know how they're going to do that. Maybe by making hydrogen, having a top, and have this in the middle. But it is an issue to think about. How do I get around that roadblock? Because chemical looping by itself is going to be limited by that just flat-out Carnot efficiency. It's peak temperature. It's not a combined cycle technology. But there are lots of other reasons that make it an advantage, right? I don't need all the extra equipment to operate. Say if I did pure oxy-fuel, I don't need an oxygen plant. You know, I could just use this, and it really does look a lot like technology we know, fluidized bed combustion. So I hope I've painted the picture here like there's pluses, minuses, there are things we know, there's things we don't know about how to design these systems, but there's genuine promise here, and we hadn't even talked about chemical looping for other applications like chemical production and other things besides raising steam to make heat. There it may have even more advantages. So we'll find out going forward. Well, I'm just on time here. That's great. So my points here today, you know, it's not entirely new with chemical looping, but a lot of people are interested because of CO2 capture. We've talked about these metal oxide and even the sulfide oxygen carrier pairs. You know, I tried to really emphasize its oxygen capacity on the carrier as well as doing the thermal balance that matters. You know, there's a lot of experience we've gained from CFB applications, but we don't know yet how to optimize these systems. So maybe some of you, you know, who are working in related areas will come and work in this area, maybe not, but hopefully I've given you enough tools to start to think about this. And you know, tonight, if you have this brilliant insight how to design one of these, I will be here tomorrow and we'll talk about even more intriguing possibilities. So anyway, thank you. I can stick around and take questions now for a whole group, or probably I want to go and eat dinner. Go ahead, yeah.
Can you just talk about any slagging or like the size of the particles that are going through this air reactor? If it's 100% reactive material and you're burning them, are they molten and do they fuse? Anything like that?
That's why I was making those points about kinetic rates. Oh, I'm sorry, the question, I've got to repeat that for the tape here. The question was, well, can you talk about these particles going up the air reactor? Are they molten? You know, do you have slagging? No, not that we've seen, because their rates are low enough we can strip the heat off into the air side. All right, and that's why I was saying you can actually design it to avoid that problem, but you need to think about it. If you take a pail full of reduced metal, and stick it in air, and air is sitting on the top of it, it will start to release heat, right? And if you don't have that heat removed, it will, you know, start to stick together. But we don't see that so far in these tests. If you use softer materials like copper, then agglomeration from molten starts to become a huge issue. Yes. Any other questions for the whole group? Great group. If not, I don't want to keep you here. You want to eat dinner. But I'll stick around and talk if you've got specific questions as well. Thanks, and we'll see you tomorrow.